pour du doctorat de étudiant. Mon nom est Guy Rolens, donc je suis directeur de recherche CDRS à Toulouse, au centre de recherche sur la commission animale. Et mes collègues m'ont désigné pour être le président du jury de cette thèse, dont la soutenance et les questions seront en anglais. Donc, dans une première partie, M. Prudent nous présentera les travaux qu'il a réalisés pour sa thèse, sous la direction de Benoît Gaudou, professeur à l'Université Toulouse-Capitole, et de Nicolas Verstappen, qui est maître de conférence, également à l'Université Toulouse-Capitole. Et ensuite, nous aurons une période de questions de la part des membres du jury, et ensuite, le jury se retirera pour délibérer. Donc, permettez-moi tout d'abord de vous présenter les membres du jury, en commençant par les deux rapporteurs. Donc, Mme Julie Dugdac, qui est professeure à l'Université de Grenoble-Alpes, Julien Pétré, à sa gauche, qui est directeur de recherche à l'INEA à Rennes. Et le jury comprend également le professeur Isuki Noda, donc, qui est professeur à l'Université d'Hokkaido, et enfin moi-même, Terrence. Donc voilà, Monsieur Ulpudang, vous avez présenté une thèse qui est intitulée Simulation and Prediction of Dance-Code Dynamics en vue de l'obtention du doctorat de l'Université de Toulouse en spécialité en informatique et télécommunications. Les membres du jury qui ont évalué votre thèse l'ont accepté pour la soutenance. Et donc, je vous invite donc à nous faire une présentation d'environ 45 minutes. Après quoi, je donnerai la parole aux membres du jury. Merci.
Good afternoon, everyone, and welcome to my PhD defense. I'm going to defend my PhD with the topic simulation and prediction of dense crowd dynamics. And here's the outline of my talk. First, I will start by introducing the background and the context of my study, and then I will present you the research question. And from the research question, I conduct a systematic review to identify a research gap in the literature. And from these gaps, I proposed several objectives for my study. And the next three sections are my main contributions, including data collection, agent-based framework, and deep learning models. And finally, my presentation will end with a conclusion and a perspective for future work. So as you see in the video, here's the example of pedestrian movements in the two situations, low density and high density. And we can clearly see the difference between the two situations. So in low density, there are a few pedestrians and there's so many space to move, and pedestrians can walk at their preferred speed. In contrast, in high density, there are so many pedestrians and they cannot walk freely because there's not enough space. And the study of this situation is pedestrian modeling. It's a research field that aims to understand, predict, and simulate pedestrian in various environments. And pedestrian modeling is a powerful tool used in various domains, such as evacuation, urban planning, event management, computer graphics, and so on. And therefore, because of various applications, there's an essential need for reliable models. And the need for reliable models is also the target that drives the MANTRAS project. It's a 3-year project funded by French National Research Agency and German Research Foundation with participation of 4 partners, 2 from France and other 2 from Germany. And the target of the project is to develop reliable models from different backgrounds, including physics-based model, deep learning models, agent-based models, to simulate and predict the dynamics of dense crowds. And one crucial factor that these models should account for is density, as it's the direct factor that influences pedestrian dynamics. The figure below here, you can see that depending on different density levels, there are different types of dynamics and phenomena, and some of them are quite dangerous that need to be avoided. And furthermore, modeling of high density situations, which is the focus of this study, face several difficulties. First, pedestrians in crowded situations behave in more complex way. For example, they can have physical interactions, or they can choose to follow neither in front instead of walking independently. And second, previous studies have reported that many models exhibit known limitations in specific crowded settings, like unrealistic oxidation or stacking phenomena. So given this challenge, and given we observe that different crowd dynamics emerge at different density interval, how I model the relationship between pedestrian movements and density, that's the research question that I have to seek answers during my study. And based on this research question, I conduct a systematic review with a particular focus on high density situations to identify current research gaps in the literature. And this work has been published in the journal Simulation Modeling Practice and Theory. And a total of 116 articles were connected over the period of 2000 to 2023. And this article will classify into 3 levels of pedestrian modeling behavior. These levels were proposed by Honggendon, and the classification results show that a few articles belong to the strategic level. At this level, pedestrian will decide where and when they want to go for their trips. 10.3% of articles belong to the tactical level. At this level, pedestrians will compute a path from their current location to predefine destinations using their knowledge about the environment. And the majority of articles belong to the operational level. At this level, pedestrians actualize decisions made from the strategic and tactical levels to move physically in the environment while handling local interactions. And the focus of research on the operational level is understandable because physical movement and collision avoidance are the most fundamental aspect, and these aspects belong to the operational level. And a closer look at the operational level, there are different modeling approaches. The figure on the left shows a hierarchical classification of these approaches, while the right figure shows the variation in the number of studies over the 2 periods of time. And we can see that in general, it shows a consistent increasing trend in the second period, with social force is the mostly used approach. And in general, there are more studies in the microscopic models and compared to the macro and hybrid models. And through this classification, I proposed several criteria that is suitable for high density situations to evaluate these approaches. And here's some notes, some example of the social force model, and details for the other models can be found in the manuscript. So with social force model, it is stable with a time step less than 0.1 second. It can simulate density up to 6 pedestrians per meter square. Higher than that, it needs to be carefully calibrated, and it can simulate pedestrian at a small to medium scale with less than 5,000 agents. And through the evaluation, 2 main research gaps I also identify. First, in terms of models, there's a lack of model that can simulate all density level. And for data-driven model, these models achieve best prediction accuracy compared to traditional models. But there are so many collisions in the prediction, especially in the crowded situation. Second, the calibration and validation of this model remains restricted due to the lack of high-density data sets. And given these given these gaps, and given we observe that density plays a crucial role in pedestrian dynamics, I proposed 2 objectives for my study. First, the first objective is to investigate the density related factors used in the hybrid approaches to develop a framework to couple models and also to improve the deep learning model. And the second objective is to collect high density data set for the calibration and validation of these models. And in the next sections, I'm going to show you how I make contributions to obtain these objectives. So in the last section, I have presented several research gaps, and I also proposed several objectives for my research. In this section, I'm going to show you one of my contribution, which is a high density data set. And these data sets were connected together with the Mantras project members, and the data paper is now under review. And so the data was connected at the Festival of Light. It's an annual spectacular event that takes place in Lyon, France. We focus on the Place de Dang-Huu, which is the city center area, and also the center of the festival and the most crowded spot. Why we choose this place and this event? It is because at the Place de Dang-Huu, there's 7 minutes show, and after each show, pedestrian will exit in a pre-configured roads, and the plaza will be refilled by new people. And in this show, they will project nice animation onto the wall, and people will gather around to watch the show. And from my viewpoint, it's also very interesting to see how a large dense crowd will exist in a controlled way. And the objective of the experiment is to capture the dynamics of dense crowds at different perspectives, and therefore different types of camera were installed to record the dynamics of the dense crowd. The video, you can see from the video, it's the video recorded by camera 1, which is a CCTV surveillance camera mounted on top of the city hall. And here it's a recording of the crowd after the end of one show, and people will move to the exit road. And you can see the arrow here. It shows, it guides people to these roads. And 4 other cameras I put on the balcony of the second floor apartments to the focus. The target of this camera is to focus on like a small area with high resolution to extract pedestrian trajectories and pedestrian outflows. And we were able to collect 200 gigabytes of videos corresponding to 8 hours of recording. And we chose the 9 best videos for the trajectory extraction corresponding to unidirectional with obstacles and bidirectional flows. And we observed that in unidirectional flow, maximum density can get up to 2.6 pedestrian per meter square, which is significantly higher than bidirectional flow, which with maximum density is up to 1.1 pedestrian per meter square. And there were a total of more than 5,000 trajectories extracted using ptrack. It's a automatic software developed by Unix Research Center. And the extracted trajectories were validated using the manual cross-checking method with independent verification from people who did not involve in the tracking process. For the outflow, we implemented the manual counting methods. So pedestrians were counted when their heads passed the reference lines, and there were a total of more than 3,800 pedestrians counted. And the instant outflow represented by the black dots can reach up to 10 pedestrians per second. And here I used the Gaussian filter method for the instant outflow to mitigate noises and improve the accuracy. And this outflow, this smooth outflow is used in the next section for the calibration and validation of my models. So in summary, in this section, I have presented the MANTRAS dataset. This dataset was conducted at the outdoor experiments at the Festival of Light Neons, and 2 types of data were collected, including the trajectories and the outflows, with maximum density can up to 2.6 pedestrian per meter square. And the data paper is now under review. You can get access to the data through this QR code. And in the next section, I'm gonna show you how I use this data set for to calibrate and validate my models. So in the last section, I have presented the MANTRAS data set. Now I'm gonna switch to agent-based modeling, where I develop a hybrid framework for pedestrian simulation. Therefore, the name HyPetSim. And this work has been published in the journal Sensor and presented in the PALMS 2023 conference. So the general idea of the HyPetSim framework is that the environment is divided into separate zones, and each zone corresponds to one model. So modeler will choose proper models for one zone, depending on density of that zone. And pedestrian are modeled at 3 levels, including strategic, tactical, and operational. And they can move from one zone to another. And when they change zone, they switch models. And to do that, I need to design an architecture that is generic and modular in order to first to capture several models for each level to adapt to different situations. And second, to allow pedestrians to dynamically switch models when they move to a new zone. For example, here, if when they move to a new zone, they will get corresponding information of models using in that new zone and update to their corresponding attributes. And through this updated value, it will automatically call the new model in the next simulation step. And I'm going to show you one practical example for this architecture by integrating 2 operational level models, including social force model and continuum crowd model. And this implementation is done on the Gamma. It's a generic simulation platform. I choose social force model because it's mostly used approach, and it has been demonstrated to realistically simulate the pedestrian behaviors in low and medium density situation. And continuum crowd model because it simulates pedestrian as a whole and using differential equations. And therefore, this model is suitable for high density situation. And by combining the 2 models, I can cover different situations from low density to high density. And in social force model, pedestrian movements are governed by a set of social forces. And there's a driving force to the target, repulsion force to neighboring pedestrians, and neighboring obstacles. And given this, we have 4 parameters that need to be calibrated, including the preferred speed, the reaction time, and the scale and the interaction range of the repulsion force. And in continuum crowd model, in this model, the global navigation will be based on the equivalent equation. And in this model, environment is discretized into cells, and pedestrian in one cell with the same target will move with the same velocity. And the pedestrian speed in one cell is defined by the maximum and minimum thresholds for speed and density. Here you can see the relation between pedestrian speed and density. And therefore, there are 4 parameters that need to be calibrated for the continuum crowd models, including the maximum and the minimum thresholds for speed and density. And I'm going to show you the coupling of this model, which is applied to simulate the crowd exit scenario at the Festival of Light in Lyon. So to do that, the environment is divided into 3 zones, including the plaza and the 2 exit roads. And there will be a total of 3,800, more than 3,800 agents that's distributed individually and uniformly in the plaza, and the simulation will end when all the pedestrians reach the end of the 2 exit roads. So because we observed that from the videos that during the exit, the plaza will experience higher density compared to the 2 exit roads. Therefore, the plaza is defined as high density zone and simulated by the CC model. And for the 2 exit roads, these 2 exit roads are defined as low density zone and simulated by the social force model. And pedestrian will switch model when they move from the high density zone to the low density zone. And to make a realistic simulation, I added TDNA. It's a delay time when pedestrians switch model. This TDNA is designed for controlling the alpha low, and this parameter need to be calibrated using the actual data. And when pedestrian exit the plaza, they will probabilistically choose one of the 2 exit roads depending on their location. Specifically, if their location is closer than the Chenavad road, they will choose this road with a probability of beta, and the other roads with a probability of 1 minus beta. And similarly, if their location is closer than the Constantine road, they will choose this road with a probability of alpha and 1 minus alpha for the other road. So in the hybrid model, we have 3 parameters that need to be calibrated, including TDNA, alpha, and beta. So in total, we have 11 parameters in the framework that need to be calibrated. And I will use the genetic algorithm method to calibrate these parameters. I choose this method because it's intuitive for understanding, easy to implement, and more important, it works well with a large continuous search space of parameters, which is the case of this calibration task. And furthermore, because it used pedestrian outflow data for the calibration, this data is not easily and directly used with statistical methods for parameter estimations, such as maximum likelihood estimation or Bayesian inference. And the GA is run with a population of 128 individuals over 150 generations to obtain the calibrated values. And from the calibrated values, I ran 90 simulations to extract the simulated outflow. And from this simulation outflow, I compare with the actual outflow, and the results show that with the outflow with only 2 peaks, the simulated outflow can qualitatively capture these 2 peaks. However, with outflow with many local peaks, it can only capture the average value of the outflow. And here the video is a demonstration of the hybrid model with pedestrian in red as simulated by the continuum cloud models, while pedestrian in blue are simulated by the social force model. So in the last slide, I've showed you the application of the hybrid model to simulate the crowd exits. In this slide, I'm going to show you a flexibility of the HyperSim framework in capturing different kinds of combinations of models. So to do that, I compare the hybrid model with 3 others combinations, including social force only. So with social force only, basically it's social force everywhere in 3 zones. One CC2 model, so it's a one continent crowd model for the whole environment. And therefore, we have the higher zone, but only one zone. But in this case, there's 2 exits, 2 targets corresponding to 2 exit roads. And the higher target in the CC model, the higher complexity. And the final model is 3CC1. So basically, one continuum crowd model for each for one zone, and with only one target. And I used 2 metrics, which are density map and computation time, to compare these models. And in terms of density map, with social force only, they can simulate medium high density, and the high density area will be observed in both the plaza and the 2 exit roads. With 1CC2 and 3CC1 models, it can simulate very high density up to 8 pedestrians per meter squared. But similarly to the social force only, the high density area can be also observed from the plaza and the 2 exit roads. On the other hand, the hybrid model, we can see clearly the difference between the difference of density between the plaza and the 2 exit roads. And this results demonstrates that by coupling appropriate models, we can improve the diversity of simulation phenomena. And in terms of computation time, the hybrid model show the shortest duration time compared to the other models of different numbers of simulated agents. So this result suggests that by coupling proper models, we can not only improve the diversity of simulation results, but also improve the computation time. So summary for this section. In this session, I have introduced HyperSim. It's a hybrid framework to couple different models, and I have demonstrated an example of a hybrid model to simulate the crowd exit at the Festival of Lights. And the framework is calibrated using a genetic algorithm method. And I also demonstrate the flexibility of HyperSim in capturing different kinds of models, different kinds of combinations. And key takeaway for this section, by combining proper models, we can have the balance between the speed and the realism of phenomena. However, this framework have several limitations. First, it used fixed and predefined zones. And second, the framework assign models for one zone depending on initial density estimation. And this model assignment does not change over the whole simulation. So I'm gonna propose several directions to tackle these limitations. First, instead of predefined fixed zone, we can use dynamic zones, and this zone can be achieved by using density-based clustering algorithm for a pedestrian location. And second, we can before the pedestrian switch models when they move to new zone, but the zone itself can also switch model in response to real-time changes of density during simulation. And in the last section, I have presented HyperSim. It's a simulation framework to couple models. And these models integrate traditional models, meaning that they are based on predefined rules. In the last decade, deep learning models emerged as a new technique to predict pedestrian trajectories. And these models have shown promising results in the low density situation, and therefore particular interests are placed on this model to see whether improvements can be of these models can be made in a crowded situation. And this work has been presented in the KIC 2023 conference. And the objective of the deep learning model is to predict accurately pedestrian trajectories over a specified time horizon. So it's a sequence-to-sequence task with the input is the past trajectories of the past positions of pedestrians over some observation time steps, and the output is the predicted positions of pedestrian over some prediction time steps. And deep learning model have gained a lot of attention from the community. The figure on the right show the number of citations of different approaches in recent years. So with social force model is still the mostly cited approach. However, deep learning models, including social NSTM and social GAN, have shown a rapid increase in the number of citations in recent years. And prediction by deep learning models has been demonstrated by achieving the best distance accuracy compared to traditional models. However, our findings show that these predictions can have many collisions, especially in the crowded situations. The video on the right show a demonstration that with the ground truth pedestrian can take the left to avoid collision from each other. Prediction by deep learning model. In the second video, they can have a very low distance error, but this prediction is unrealistic because there's a collision in the prediction. On the other hand, we can train deep learning model to predict in this situation that they can take the right to avoid each other. With this prediction, we can have a high distance error, but in this case, it's realistic because in terms of physics, because there's no collision. And I look at the literature to find out the reasons why deep learning exhibits the collision problem. And I found several reasons. First, the mostly used data set in the literature is low density due to the lack of high density data set. And second, deep learning models have only collision mechanism in the architecture, while the loss function, they primarily focus on minimizing the distance accuracy. So given these reasons, my idea is to penalize collision-prone trajectories in the prediction by modifying the loss function. So I do not change the architecture, but focusing on improving better loss. And I look at the literature to find a well-known term that describes collision, and I found TTC concept. So it's the matrix that estimates the remaining time before collision of two pedestrians if they keep moving with their current velocity. And fortunately, Kazamuzat have did a great work by using TTC to investigate the interaction law between pedestrians, by developing the time to collision interaction energy. And this energy is defined by the mutual repulsion of that prevents two approaching pedestrians from collision. And I'm gonna use this idea to improve the loss function. So in my proposed loss function, I still keep the first term, which is originally in the deep learning models, that minimize the distance error between prediction and the ground truth. And I added the second term, which for the collision loss term, and this term calculates the sum of the average of the hyperbolic tangent function of the interaction energy. I use the hyperbolic tangent function to normalize the Nash value when TTC of energy when TTC is so small, close to 0. And I added a collision weight term to investigate the impact of the second term on the prediction performance. And in the experiment to evaluate my proposed loss, I have different data sets. The first data set is the low density, which UCI and ATH. These data sets are mostly used in the literature. And I also have the Mantras data set, which are high density. And the data I train separately the low density and the high density data sets to predict the trend with 9 observation time steps corresponding to 3.6 seconds, and to predict pedestrian trajectory in 12 prediction time steps, which correspond to 4.8 seconds. And I have different value of collision weight of lambda from 0 to 2 to see how the collision loss term will work with different weights. So for the evaluation of the predictions, I proposed 2 metrics. First, it's a distance matrix. I used ADE. This matrix calculate the average distance between the predicted trajectories and the ground truth over all prediction time steps. And for the second matrix is for collision, and I used the collision matrix, collision 1, that calculates the percentage of the prediction scenes that have collisions. And here's the quantitatively comparison, qualitative results by comparing the social NSDM and the TTC SNSDM with lambda equal to 1. So in the social NSDM, in the prediction of social NSDM, we can see the collision happen here, right here. And on the other hand, with TTC and SDM, they can address this problem. And for the qualitative results, in the low density data set, we can see that the collision results reduce significantly, while the ADE remain quantitatively stable. And here in this scenario, the best lambda for low density is 1, and in high density data sets, the collision results reduce significantly until lambda gets 0.5, and when lambda is higher than that, it's increased rapidly again. For the ADE, the higher lambda, the higher ADE. So we have different results in the low density and the high density data set, but we can see with some lambda we can get positive result with significant improve in the collision matrix. So in summary, in this section, I have presented the TTC SNSDM with the new loss term. I added the second term in the loss and also desired a collision weight for this term, and the results show that the collisions is reduced significantly, but different trends are observed in the low density and high density data set. And key takeaway for this section, by adding TTC interaction energy to the loss function, we can have more realistic predictions with lower collisions in the predicted trajectories. And for future works, I propose several directions to better understand the collision loss term. First, it is necessary to investigate the impact of the loss term on other networks, such as GANs or NSDM variants. And we can also need to develop a general approach for defining the optimal lambda for each data set. And finally, it is so interesting to see how which cognition mechanism that is learned from the loss function. Is it acceleration, deceleration, or steering behavior? So I have presented my whole process of research from conducting a systematic review to identify research gaps. And from this research gap, propose several objectives for my study. And I have presented you my three main contributions, including the Madras dataset, the HyperSim framework, and the TTC SNSTM deep learning model. And I used knowledge from various domains for my study. And in turns, my contributions are back to this domain, including pedestrian modeling, agent-based modeling, and deep learning. In pedestrian modeling, I have contributed a systematic review with a particular focus on high-density situation, the Madras dataset. So together with the Madras project members, it's the high-density dataset, and it addresses the lack of the high-density dataset in the literature. And the HyperSim framework to couple different models based on density, and the TTC SNSTM, it's deep learning model to predict pedestrian trajectories with low collisions. In agent-based modeling, I have contributed the HyperSim's architecture. This architecture can be extensible to simulate different kinds of dynamics, such as traffic or social simulation. And in deep learning, we have identified the issue of collisions with deep learning model in the predictions. And in the future, I have several targets. For short term, I plan to integrate more models into this framework to make HyperSim a useful simulator for decision makers to test and combine different models for different situations. And one of the models will be the TTC SNSTM. With this model, I can use low lambda for low density zone and high lambda for the high density zones. And for long term, one promising direction from my viewpoint is combining the simulation and deep learning. Using one model can boost the performance of the other model. For example, in agent-based modeling, agent now can have intelligent behavior that trains from deep learning. And that's the end of my presentation. Thank you for your listening.
Thank you.
Thank you.
So now we are going to have a discussion with the luminaries, so we are going to listen to the reference.
Yeah.
I can see one.
Thanks, Nico.
Okay, so thank you, Mr. President, for the introduction, and thank you to the supervisors for the very kind invite to be on the jury. I'm really happy to be. Thank you for your presentation and also for your manuscript, which I thought was very good. I'm very happy with your work.
Thank you.
Manuscript was compact, but it was very complete and it was very interesting to read. And I think you've done some really nice work. In particular, I was impressed with your public release of the high density pedestrian data set. I think it's a very valuable contribution because we're missing these kinds of data sets. And also your hybrid framework for coupling the models is a very, very positive contribution. Also, I think the value of your work is being reflected in the high number of publications that you've had, which I think is very commendable for somebody at your stage in the career. So well done on that. So
Thank you.
I'm going to go in and start asking some questions. At the end, you mentioned that your agent-based simulator can be used by decision makers. And one thing that struck me when I was looking at the video there, it is the realism of the behaviour, because something sort of worried me a little bit about how you've been modelling. So things like the exit choice behaviour. So an agent will choose the nearest exit with a probability. I'm not sure that that's always the case, because I think things like it tends to depend on, for example, where I've parked my car.
Yeah.
You know, I'm not going to choose the nearest exit. It depends on quite a lot of other factors. And the idea that your simulation seems quite clean. Everybody's moving at the same pace, the same speed. And from what I can see, it looks like everybody exits the square. I just wonder if you can comment a little bit on how you see the realism of the simulator.
Okay, so first, maybe I need to a few seconds.
Yeah, reflect.
So the calibrated first the calibrated values for these probabilities show that pedestrians tend to choose the nearest exit roads instead of the other road with the high probability for the nearer road. And I think compared to the real situations, it makes sense because normally they prefer the near exit road. But unfortunately, we cannot extract this kind of data in the videos because it's very difficult to count pedestrian at the bottleneck because there's very dense and sometimes we cannot see where is exactly the pedestrians. But we for the outflow, we can see that with these probabilities, it can quantitatively capture the outflow. So we can evaluate this behavior just through the macroscopic data like the outflow. And fortunately, we don't have the microscopic data like real probability.
I guess also that maybe that the video data that you have could also be complemented with questionnaire kind of data. So you ask people, you know, where did they come into the square, where did they exit the square, and why?
Yeah.
So then maybe you can have a complementary form of data in addition to the video data could be an issue.
Actually, we have this kind of questionnaire in the experiment here because it's the scope of my study. I didn't present it, but we have something like questionnaire and the GPS data. However, because here in this scenario, we cannot because pedestrian will exit in a controlled way, meaning that there's no pedestrian don't have so much decision to make. So we ask different kinds of question, but not for the exit. Yeah.
Okay. Yeah. I mean, I think, you know, these things about the realism could be quite easy to fix. So, for example, with the walking speed,
yeah,
you know, that we can easily change the the speed of the agents. And it's true that in a high density situation, agents tend to move along as a mass at the same speed. So I think that's quite easy to change without
Okay.
a great deal of difficulty. Okay. Also in your simulator, in your thesis, you mentioned that there was a sensitivity to some parameters. Could you explain what parameters they were and what we could probably do about it?
Yeah, I have some slide for this. I think here, wait me a second. With this, so I conduct a local sensitivity analysis for different parameters, and with the hybrid parameters here, beta show the strongest influence in the fitness function, and with social force model, it doesn't affect. So their contribution is trivial to the fitness function, and with the continuous crowd models, only parameter related to speed shows the strong relation with the fitness function. On the other hand, density factor, it didn't show any impact on the fitness function. And I think with this one, because it's directly influenced the speed of the crowd to the two exit roads. So this is understandable because it will decide how fast the overall crowd will move and how closer they reach the exit. So which directly affect the outflow of the two roads. And here for the hybrid model, beta show stronger relation to the fitness function, because I think it's also very like specific in very context related. Like if you look at the simulation, so I think that there are more pedestrians that closer than to the channel rat road. So there's just the vertical roads, exit road. So therefore, the value of beta will be so beta. So pedestrian in this case, like there's a high probability of pedestrian can move to the other roads to balance the outflow of the two roads. I don't know if it's clear or not.
Yeah. I mean, I'm just thinking from a realism point of view, if I was leaving a very crowded square and I see one exit road that's really packed and another exit road that's not, there are not that many people, I'd take the road that's not very dense and then try and find another way back to where I wanted to go. I think just logically as a behavioral choice, I think that's probably what people would do.
I think there are also some real world experiments showing the faster is slower effect. So if we all pedestrians choose the shorter roads, it will be so crowded and congested, and some of them can. On the other hand, we choose another road and we can move faster.
Thanks.
Thank you.
Yeah, I mean, another point is about the calibration of your model. You used a genetic algorithm approach, and I think you explained very well about the advantages of doing that and why it's a good choice. What are the problems with using that approach? What is not good in using GAs?
Okay. I think this method is quite easy to understand and easy to implement. Using GA, I think with this method, we should only use the macroscopic data, meaning that we compare it with macroscopic data like the alpha low, and we could not use we could not use, for example, if we use the statistical method, we need some microscopic data, like for example, trajectories to directly estimate like the walking speed of a pedestrian, or like to estimate the reaction time. So with these parameters related to microscopic aspect, we need microscopic data. And with GA, I think we don't have, with trajectories, for example, if we have trajectories, we cannot directly use GA to, or we can, I don't know, we can also simulate pedestrian trajectories and compare this. But from my point of view, macroscopic data can provide a global global results. So yeah. Yeah.
Okay. Okay. I'm going to throw in probably an unusual question.
Yeah.
There's been quite a lot of criticism with simulation and deep learning in its effect on the carbon footprint and how it affects climate change. So, for example, with deep learning, there's been a lot of criticism that it's actually very bad in terms of how it can affect climate change, because it uses so many resources and so much electricity, etc. What are your thoughts on that? Sorry,
it's a really open question. So you mean that we train deep learning models on like a huge number of computers with like high performance in computing, and it could cause like many like okay. I think we always have to pay some trade-off between different objectives. On the one hand, we can gain like very intelligent technique, and for future development, like self-driving cars or something like that, or ChatGPT, something like that. On the other hand, there's some drawbacks. Well, first, it's related to the environment, or like some people, they can lost their job because of like very intelligent and automatic machine. But we have to pay the balance. We have to pay the trade-off, and that's my idea. And I think that's also the natural development of technique. So
okay.
Thank you.
Thank you very much.
Thank you very much. Okay, thank you.
Thank you.
So I would like first to thank you all for inviting me on this jury. Just like Julie, very happy to participate to the defense. I would also say something about your work. I'm quite impressed by the fact that in this short time of a PhD, you dealt with those different topics of collecting data, do a model and simulation, do a nice survey as well on the topic. I think you made a good work at writing this survey, and also coming with two ideas about simulation and modeling.
of course, this raises many questions.
Yeah.
The drawback of doing this. I will start with the last part, actually, the very last part.
Okay.
Using LSTM to simulate crowds, not on the carbon print aspect, even though that's an important question for me. But also in terms of technical choice as LSTM for a valid architecture to simulate this. Let me explain.
Okay.
So actually, even Alain himself criticized this choice, right? He made this paper where he is attacking his social STM solution, and he demonstrates sort of that it doesn't work. It's not able to learn collision avoidance very, very well.
Okay. Yeah.
I read this paper, and I think one main explanation is that LSTM is trying to say that all what is coming next in the trajectory is explained by, or is explained by the past trajectory. So, and mechanically it's valid, right? The past trajectory tells you how you walk, which speed, which direction, what is your goal probably. So it embeds all this kind of information. But collision avoidance is about the future and not the past. So, and there is nothing in the past trajectories that tells that you will meet someone and will avoid him, right? So, and you decided to still choose this architecture as a solution and to extend the way it's trained to embed this information about the future, which TTC is conveying to the learning process. Okay, my question is simple: is LSTM a good pick?
So I think it's not the best pick, but it's a good start, because NSTM is the most famous and the pioneering deep learning architecture. And because my focus here is the loss function, not because I did not change the architecture. So NSTM is a good start, and it shows improvements. And because my contribution is the loss function, so I can use it and investigate this loss function to another deep learning models. And this is also one of my direction for future work, to investigate deep learning, the loss function in more recent models. So it's, for me, it's a good start, but not the best one.
What would be the best one?
I don't know. I need to check at the literature for more recent models. I don't know. I'm not so sure when the best one. Yeah.
Okay. I had also a question about LSTM, but maybe let me check. Yeah, I think that also another reason why LSTM was not really able to learn collision avoidance was probably the lack of data.
Okay. Yeah.
At the moment it was published. So since you collected other data, I guess you used the Festival des Lumières dataset as a training dataset for your TTC LSTM technique, right? So I'm not sure I remember this in the manuscript, but did you compare if using the Festival des Lumières dataset improved already social LSTM? The vanilla version, or this is not the question you went through?
So I have, so basically I have TTC SNSTM with different value of collision weight, and with collision weight is 0 here. So it's exactly the social NSTM, and it's a comparison. So it's a social NSTM is the baseline with lambda is 0. So I did compare with the results, and it show improvements in collisions.
Okay, so yeah, with lambda 0, you get back to the
because we have exactly the same loss function.
Makes sense. Okay. Okay. now moving, so I'm moving backwards in your,
Okay, yeah.
in your manuscript. So this hybrid model you proposed.
Yeah.
Let me, so I think I put this in my report. Like the very first question I have is how does this continuum model is working exactly? So you are because let me explain. You try to combine two different models, but they are not of the same kind. One is an Eulerian model, the other one is a Lagrangian model.
Yeah.
So it's like already to me, it's sort of weird to do this because you have complexity here, especially in the switch. So how does it work exactly? Are you running still a particle model on top of the continuum model?
So,
And then, so how do you switch from the CC zone to the SFM zone exactly? How do you come with a continuous representation of the crowd to a particular representation of the crowd?
Yeah. Okay. So first, continuum crowd models is a type of model that combine both macroscopic information because they use differential equation, and this information can be used for the global navigation. Like one cell, they can have the general direction to the target, and pedestrian, and it also represents individual level. So basically, just for the presentation of pedestrians. So pedestrian in one cell, they will choose this direction, and they also with the speed is defined based on the local density, and there's a special mechanism to avoid collision the collision of pedestrian in each cell. So it's from the agent-based modeling perspectives, it's kind of a mesoscopic model, meaning that they combine both macroscopic information and individual information. So in this model, we still have individual level representation. And
let me ask if this is a very similar version to the Troy and Popovich paper. I see you had this citation, continuum crowds. I think it's the title of the paper.
Yeah, continuum crowd. Wait me a second. This one, yes.
Yeah, okay. So you would say that your continuum model is very close to this one, right?
Which one? Sorry.
The one you cite at the bottom.
Yeah, it's this one. Yeah.
It's the exact same.
Exactly the same. Yeah.
Okay.
And so when pedestrian move from continuum crowds model, so it still have individuals with velocity, with location, and when they switch model, basically, so it's still have individual. So I keep the information of the location of pedestrian, and apply the social force for the next simulation time step. So it's not the same as combining the macroscopic model and the microscopic model, because in this case, you need to have some mechanism to aggregate and disaggregate of these models.
There was a paper in the same conference 3 years after describing this copying process. So I'm not sure if it's in your list of reference, but something you can check if you're interested.
Okay, yeah, thank you.
Still, you are moving from a uniform crowd because continuum crowd is modeling on a uniform crowd, all particles the same.
Yeah.
Well, unlike in the social force model where you can have different destination, you can have different parameters for each particle. So still that's still an issue that I see, that you combine the model of a uniform crowd with a model that can go more towards diversity. So that's more sort of a problem.
Okay.
And if I can also ask, why the social force model?
Yeah, it's I should pick one and I look at the most famous one. And because my idea is to use one microscopic model for low and medium density, which to simulate the pedestrian on the exit road. And I think social force model can also do very good job with the collision avoidance mechanism by forces. So, yeah, and there also another model like one from Kazan-Musas. It also work well. But yeah, I think everyone is familiar with social force, including me. Yeah, so I choose.
Yeah, but what surprises me is that then doing this, we as a community sticks to solutions that were also proved to be wrong in some cases. I mean, that's social force model is now 40 years old, and since then there were many improvements. In
yeah, I agree. But
okay, so that would be great if we continue in this direction and that you maybe reconsider this choice and see if there is an interest in moving to something else on it.
Yeah, thank you.
Yes, and yeah, I think I also pointed the fact that another way to see this combination of different models would be also more like a switch in different, so keep the same model and also more try to switch policies instead of switching models. So did you consider this comment? And
I read this paper and thank you for mentioning a very interesting paper. And in this paper they did a great work by dynamically choose proper model depending on the context, and they use the quality function which take into account various factors for choosing the proper models. For example, including like individual factors, interaction factors, and global factors. So it considers various many factors. It definitely improved the simulation accuracy. Compared to my research, I use only density factor because it's directly represents the global feature of the dense crowd. So if I look at the dense crowd, the first factor that come in my mind is density, and using more factors can definitely improve the accuracy. But in large scale simulation, it can also increase the simulation complexity, and because sometimes I have to balance between the accuracy and the speed, so I just use just keep it simple by using only density. But definitely there are some very interesting factors that I should look at in the paper.
Actually, that was my next question, so I won't ask it. If there is something else than density that could explain it.
Yeah.
Okay, let me ask like two last questions. One would be so still going back in your manuscript. So the data set itself.
Yeah.
So you mentioned it was a joint effort. So I think you were not the only one taking decisions here, but probably you had discussion as a consortium about this. Okay, I know how complex it is to collect field data, but let me ask, what was the idea, or what was the intention behind choosing this specific event, specific location, and specific kind of data? So you decided to go for trajectories and navigation kind of decisions. But okay, what about the situation itself? What was the kind of knowledge you were expecting to bring by collecting data at this specific place?
Okay. Let me 1 second. So I think so in this scenarios, so it's high density situations. So what we observe is that pedestrian behavior, so they behave so differently in the crowded situation. For example, like in the festival night, there's so many people walking in groups, normally from 2 to 5 people, and their walking speed also vary significantly. So the majority of people, they walk at normal speed, but some of them walk very fast, or even some of them run. And so many people walk with items such as the baby stroller, the balloons, and walk with the phone when they are looking at the phone. And also, we observe that in unidirectional flow, it typically achieves higher density compared to the bidirectional and multi-directional flows. And I think some of them is very unique in this experiment, the scenario, like a large dense crowd move in a controlled way, and even some people, they decide to stand still, they want to watch the show again. And when the new people come, they have to avoid these standing people. So it's very unique in this experiment. But yeah.
I will ask a last question, still about the data set. So you have shown how you are using this data set with your own work, but okay, say you have 1 more year of PhD. What do you do next with the data set?
Okay, yeah. So the data set can be used in the various objectives. First, it can be used to understand pedestrian behaviors, like understand grouping behaviors, for example. So first, the first target is to understand pedestrian behaviors, especially in crowded situation. For the simulation models, it can be used for the calibration and validation. Also for deep learning model, they can train this data set for high density situation. That's the use of trajectories. For the outflow, I think they can use it to test the capacity of the plaza, and also to simulate exit scenario, and also prepare some safety control policy for the event management. So it's I think it's maybe the potential usage of this data set.
Okay,
thank you.
Thank you, Jean. Now, Professor Noda.
Yes. So thank you very much for inviting me as a jury, and also I'm very glad to to examine us for your thesis.
Thank you.
And so maybe I'm from the engineering domain, so I have several questions about from the viewpoint of engineering.
Okay.
And the first question is so what is the target application of this simulation and models? Because I ask because from the engineering, modeling and the simulation based using the model is depend on the application. For example, evacuation for the evacuation from the disaster. Evacuation for the evacuation time is most important.
Yeah.
And the collision is not matter. But in the case of the design of event, the comfortability of the passengers is important factor. In that case, collision is the matter, but the time is not so serious matter. So therefore, if you design the simulation, you need to image some target application. And in this work, what is the target application?
Okay. So first, so this the high-passive framework simulates pedestrians in high-density situations, but it's in non-emergency situations. So it's currently the application. I think this framework could be used to like simulate different scenarios and we to check the safety policy. For example, like they test different models and they check the evacuation time and by these models they can have like evacuation policies. So it's one of the potential applications of HyPath-Sim. Yeah, for the evacuation, for safety control and event management, I think it's one of the direct applications. But currently, now it's simulated in non-emergency situations.
Okay. Okay, so the second question is related to the page 23 or 4 in this slide.
Sorry, which?
23 and 4.
23, okay.
Yeah,
This
so
one.
in the social folder, so you define this kind of thing, and for the next page.
Yeah.
Maybe it's 24.
24, it's
Continuous.
continuous graph.
So from this equation, so I think it that cannot reflect the hysteresis. There's a asymmetricity of forming density area and resolving the density area. It is usually in the real phenomena of pedestrian. Forming density area and resolving the density area is not the symmetry phenomenon. This is different process. But from these equations, I guess this phenomena is symmetry. So how to handle this kind of differences of asymmetry using these kind of equations?
You describe your question again because I didn't get your idea. Sorry.
So for example, for example, clouds start to gather, then it forming the density area. But the process of density area is quite quick.
Okay.
But resolving process. So the density, from the density area, so the pedestrian is leaving. In this case, the process is relatively slow. It is also again very natural phenomenon in real world. But if we follow this kind of equations, this kind of process is symmetric. The speed of forming and resolving will be the same.
Sorry, I still didn't get this.
I
Maybe
think it's to do with the when you're forming a dense crowd,
yeah.
there's that process, and then when that dense crowd dissolves,
Okay.
there's another process which it gives a symmetry. I think your questions about the symmetry of those two processes, and I think the question is that maybe these equations don't represent accurately that this symmetrical process of how those crowds form into a dense mass and how they dissolve into a less dense crowd.
Yeah. I think in this model, there's a special mechanism to estimate the density for each cell. So they don't use the discrete function for density. For example, here for density in each cell, they would use kind of how to say, it's like a density distribution. So pedestrian density in one cell, but they also take the density of the adjacent cells, so to smooth the density distribution over the whole environment. And by this mechanism, they can update the real-time changes of density. And I don't know if I answer correctly your question.
Okay, maybe it's I can understand.
Yeah, thank you.
Okay, the next question is that related to page 26.
Okay.
Yeah, so in this case, so you try to combine the two models
Yeah.
by zones. And in this case, there is a problem of gap of flow speed between at the boundary of
Yeah.
zone. So because the calculation of each zone is different, so the flow speed may change, may different. So how to resolve or how to handle this kind of problem in simulation?
So first, I agree that when we switch model, there's a like huge difference between the instant velocity between the two models. Unfortunately, I don't have the mechanism to smooth this, but I will propose like a reaction time that they can switch gradually to the new velocity to smooth the trajectory to avoid unrealistic like suddenly changing behavior. That's my idea. Yeah.
And this is the same question. In this case, you show the case only the case from density area to low density area.
Yeah.
And is it handle the reverse case from the low density area to density area?
Okay. Yeah. I think yes, in this situation, for example, if they move, so basically in the scenario, they move from the plaza to the two exit roads, but assume that if they move from the two exit roads and to the plaza, because we still have, for example, individual enter this, the new environment, and the continuum parameter can capture this information and integrate it to this cell, but to integrate the pedestrian information to this cell and then compute the new velocity field and density field for these cells. And I think this, yes, definitely yes, yeah.
And about so the 27, page 27.
Yeah.
Yes, so I like to know what is the concept of this fitness function? So it's what kind of feature or phenomena you are focused on using this fitness function?
Yeah. So this fitness function we can calculate the average absolute normalized error between the simulated outflow and the actual outflow. And so basically, it use two features. It use two variables, which are the actual outflow and the simulated outflow. And from this fitness, they will obtain a better individual for the next generations. And
my question is that I understand the equation.
Yeah.
How if the model improves this fitness, then what kind of phenomena is changed in the simulation, and how to what kind of feature becomes closer to the reality?
what kind of feature?
Feature.
Yeah.
Not the data itself, but what kind of feature. So total speed or the average speed or the total time or something?
I think it's the exit time. So if we look at the validation, we can see that the simulated outflow can also achieve similar exit time compared to the actual outflow. And yeah, I think it's because it's macroscopic features. So the exit time.
Okay, I see. Yeah, understand. Okay. And you, so this is to page 30.
Okay, yeah.
So in this slide, so you compare with the differences between models.
Yeah.
But how about the comparison to real data?
The real data.
Yeah.
Okay.
So I'm not sure. So which one is very similar to the real?
Yeah. First, in this section, I'm gonna what I focus in this section is to demonstrate the flexibility of the high passive framework in like capturing different combinations of models. Unfortunately, we only have the qualitative data because we observe from the videos, and so we use because we observe quantitatively that the plaza is the density in the plaza is higher than the to exit roads, but we don't have the quantitative results. We try to estimate the density at the bottleneck, but because it's really like difficult task because pedestrians' heads is so difficult to extract from the large the CCTV video. We try to use p-track software to count and extract pedestrians, but it doesn't work. So we don't have the quantitative results. So we don't have the real data to compare. And also the main focus on this is just to show that the hybrid framework is flexible enough to capture more different kinds of models.
Okay. And so the last question is also 45.
45, yeah.
Yeah, so maybe so you mentioned about integration of the two framework and low density and high density.
Yeah.
And so in this case, so you mentioned only the density, and but the density is just one of the data or statistics in real data, but also we also have several different kind of things. So, so density is only the key factor, or you should consider another variation like speed or so wideness of area or something. So, why you choose only the density?
Yeah. So it's a similar question with Junior and Petre. I think, I choose density because if I look at the dense crowds and I choose only one factor for as a criteria to switch model, so I would think first about the density, but also very like for like in the work that Junior and Petre has mentioned. There are several criteria that also important, and depending on the target of simulation, you can choose different criteria. So in the future, I look at like the characteristics of the flow. For example, like it can be one factor. Like if it's unidirectional, use one model, and if it's a multi-directional flow, I use another model. So it's really related to the dynamics of pedestrians. It could be interesting, but here I want to keep it simple with only density factor, because my simulation is with very large number of agents. And if we integrate two complex factor, it can also the computation time will increase rapidly.
Okay, thank you.
Thank you.
Thank you very much. So, Michael, so first I would like to thank you for the invitation. You are the advisor, of course, the member of this thesis committee. Thank you also for the nice presentation.
Thank you.
I have several questions and remarks.
Yeah.
My first question concerns the condition in terms of density, which require to change the model of the pedestrian behavior.
Yeah.
So I can understand that it is necessary to change the model, especially when the density becomes quite high, and in particular beyond 4 pedestrians per square meter. The work done by Siegfried in 2005 and Elvin in 2007 showed that up to a density of 4 pedestrians per square meter, you can observe a laminar regime, right? With a minimum speed around 20 centimeters per second for the maximum density, which then increases more or less linearly as pedestrian density increases. However, in all your work and in thesis, we consider that beyond 2 pedestrians per square meter, there is a high density condition, which will become required to change the model. How can you justify this choice, especially in the light of the work by Siegfried and Elvin? Because we know that beyond 4 pedestrians, in fact, well, we are in a laminar regime, so we do not really consider that this corresponds to a density condition.
Okay.
So how can you justify that?
Yeah. So first, what you mean here is when the density is like around higher than 4, yes, stop and go ways.
You have a laminar flow up to 4 pedestrians per square meter. I don't know where this graph come from. Is it something that you draw by yourself?
Yeah, I draw by myself. I choose this interval because it's in the number in the literature. So they show that with, like, for example, density higher than 2.8, so graph will decrease. With density higher than 4.3, there's a stop and go waves start to emerge. So it's
yes, but what I want to say is that beyond 4 pedestrians, we are still not in high density condition, because in that condition, of course, you still have some social interaction, but you don't have a physical interaction, right?
I'm not so sure. I'm not so sure we can. It's 4 pedestrian per meter square here, or something like this. Sometimes it's don't have a physical interaction, but I mean the definition of high density will be based on different contexts. For example, I choose density is high. I define density is high when it's higher than 2 pedestrians per meter squares. So I based on the pedestrian movements. So at this density level, pedestrian movement, most of the pedestrian movements are constrained, so they cannot move with their preferred speed, and their dynamics, their preferred speed is influenced by the surrounding pedestrian, and that's also one the review article have mentioned that. So I pick up I pick this this number.
If you go back to slide 10,
yeah,
you mentioned that there is an act of model that can simulate all density levels.
Yeah.
I slightly disagree with this statement. In particular, I'm pretty sure that the models that Julien Peltier developed, for instance, or the heuristic model that we developed a few years ago with the Mussolini and the recent model,
Okay.
is working for a huge range of pedestrian density, including very high latency. So, well, I'm not really.
Yeah.
I don't really agree with you on that.
Yeah, because
issue.
what I mean here is like to simulate and cover all the crowd phenomena,
Yeah.
including both also collision avoidance, stop and go waves, and all the phenomena.
Yes, so
There's one model.
The model that we
Okay.
did, really, we reproduce this huge diversity of
Okay.
Yeah.
But also in terms of phenomena, in terms of dynamic.
phenomenon.
Okay, so it's I need to check that.
What I mean is that we don't have to, with the existing model, we don't really need to change.
Okay, yeah.
Then this brings me, in fact, to the validation of the hybrid model.
Yeah.
Well, I come from a different field of research, and in fact, to validate a model, we required a lot of measures.
Yeah.
For instance, it would have been interesting to have the density distribution of pedestrian, the density, the distribution of pedestrian working speed,
Yeah.
the distribution of density fluctuation. So all this, I think that all this density will be very important to validate the model.
Yeah.
Right?
Yeah.
And then I have a question. Go to slide 30. Because here, you think that this corresponds to what you observe in the real observation.
Yeah, qualitatively, because I don't have the quantitative results for the density, but yeah.
Go back to the video.
Yeah.
The video of the plaza.
Okay.
What strikes me here?
Not here. This one. This one.
Yes, here. What I found particularly striking is that here you have a plaza where you have a lot of people. Okay. But the plaza is not emptying. In your model, you are simulating a plaza where all the people, where you have a fixed number of people in this simulation, and all the people move and go to the exit street. And so you are simulating an empty phenomenon.
Yeah.
Why this is not the case in the observation?
So
this is why, go back to slide 13. And for me, this is why you observe this particular structure. Here, in particular, for instance, look at this is particularly striking on the first line and the 3cc was
this one.
Model. Look at you have this kind of lines, kind of bands of density bands.
Yeah.
This is not something that you observe in the real phenomenon, right?
Yes, I think so. Yeah. So first, the simulation scenario is artificial, meaning that not trying to mimic all the real information in the videos. Like there's still standing people, but here we don't have some situation like that, and even the capacity of the plaza, it could be much higher than 3,800 agents.
Yes, I mean the fact that the plaza is not anti-loop. So there is a continuous flow of people moving into the plaza, and then the people move to the exit street. I think this changed a lot of the dynamics.
Yeah.
So you are simulating an artificial scenario, but you want to compare to make a comparison with real data where the phenomena is completely different. Look at slide 28.
Okay.
And for me, that was a problem. I don't know if
28.
if you agree with me. And this explains, in fact, the decrease of the outer field
Mm.
in both situations, because you are simulating an emptying phenomenon. All the people that are in the plaza, they move.
Mm.
Okay? What would happen if there were more people coming into the plaza, so you're not simulating an emptying phenomenon, right?
Yeah.
Like observed in the
Yeah.
Did you try to simulate that?
Not yet. Yeah. I just focus on the exit pedestrian. So
Yes, but the exit pedestrian, in the end, this will reflect the dynamics of that you have on the plaza.
yeah, yeah,
You agree with me?
yeah. Qualitatively,
So-
not.
Right.
Yeah.
So for me, you try to make a comparison with the phenomenon where the plaza is not emptying,
Mm.
with some simulation conditions where we consider that the plaza is emptying. And
Mm.
probably this will affect the connectivity dynamics.
Yeah.
So that was my main
Yeah, yeah,
decision.
I agree. Yeah,
If I,
yeah. Thank you.
Um, okay, check. Yes, in the hybrid model, you have these two parameters, alpha and beta.
Mm.
Can you go back to the
Yeah.
So why do you consider these two parameters? Why not just alpha? Because at some point,
Yeah.
the pedestrian, when they arrive
Okay.
sections, they have to decide to go to the Constantine Road and to the Chemin Road. But why do you need these two parameters?
Yeah. Yeah. So basically, I use two parameters. So it's more complex way. It's more complex compared to using just only one probability.
Yeah.
Yep. And I think the idea is to mimic the two peaks, these two peaks in the Constantine Road. If we have similar probability, so maybe we can have something similar with the Chenavad Road with the same probability. That's my impression. With alpha and beta, we can mimic the two outflow in a different way. For example, here the value of alpha and the value of beta is different. I'll show you the calibrated results for the parameters. So alpha and beta, we have different probability. With beta here is the lower probability compared to alpha, and this lower value is can be explained by the fact that so basically there are more people closer to the Chenavad Road at the location of the exit. And then therefore beta would be, there's a portion of pedestrian who choose the Constantine Road to balance between the two outflows. So what I mean here is that because it's rectangle and because there's more pedestrian closer than this road, so beta here, it's the value for the beta is lower than alpha, so it will make people who choose this road, which is.
But this in fact go back to one of the questions that was raised by Julia Pepe, which is in fact the interface of the two models. So
Yeah.
For me, you don't really need a particular, well, you don't really need two parameters because
Okay.
a priori all the pedestrians are the same in the continuous models. So they are leaving the continuous model, and then okay, there is a quality to choose one road or the others.
Yeah.
So how do you choose the pedestrian that will follow the rule with the alpha parameters and the pedestrians that follow the rule with the beta parameters? Are they in same proportion?
I choose probabilistically. So there's a probability of so they would choose one road with a probabilistic,
Yes.
and it's not the case they choose the other road.
So it's just one probability.
Yeah, for one probability for pedestrian closer than this road, and also another probability for pedestrian whose location is closer than the Constantine road. So we have
Okay,
yeah.
What is the parameter that you choose to decide closer to that road or closer to this road? So you have to choose a distance.
Yeah, based on the distance to the nearest exit
Yes,
road.
In a much more concrete way, the pedestrian exits the continuous model.
Yeah.
So you have a probability to be closer to one road or another, right?
No, not probability. I based on pedestrian location, and using this location, choose a probability for the nearer roads, nearer exit roads. Yeah.
I just have a question regarding the large scale view of the coordinate and that's the.
Yeah, that's the data for.
So as I understood, you don't use this data to calibrate the continuous model, right?
Which data you mean?
The data on plats, the plaza.
Yeah, it's just to provide the overall or natural view of the dense crowd. I use only the orthogonals for the framework.
So how do you calibrate the continuous code model? With what kind of data?
In fact, in the simulation, it's a little bit different compared to the real situations. In this situation, I turn it. In this situation, the new pedestrian exit and new pedestrian who enter at the same time, and also there's some standing still pedestrians, so it's quite complex. And because my simulation is the situation is different, so I cannot use easily and directly this one to validate my simulation. But I think there's something that I can try to extract, like at the bottleneck, some like the high density area, like some kind of semicircle or area. So this one can be used to evaluate the simulation. Yeah.
Okay, you don't really have data to calibrate the continuous code model, right?
Yeah. In fact, we try to extract some pedestrian in this one, but with our software, the P-track software, it doesn't work because it's a very like large view and pedestrian is so small. Sometimes they overlap with other pedestrian, and then we lost the tracking, so it didn't success.
The software that you can extract the levels.
Yeah.
So that might be a way to.
Yeah, like the optical flow method.
Okay, thank you very much.
Thank you.
Stop here. So now I'm going to leave the floor to the supervisors. Who wants to start?
So thank you, Mr. President. First, I would like to thank you for accepting to expertise the works of two. And obviously, I want to thank you too for all your work. It's been pretty amazing to work with you during those 3 years. Not only you're a joyful people, so it's very pleasant to work with you, but you've done a lot of things and you've got further, further than we expected. So just to give some details about the genesis of your PhD, it was basically 2 pages where we said that as computer scientists, we feel that there are a lot of models that exist, and each model has some specificities which works well on some specific situation. And we say that, okay, we got this platform, which is Gamma. Can we try to put them all in the platform and try to combine them according to which situation? So what is very good from all your feedback is that we have this insight, and what you said, what you asked, confirms this feeling that in each specific situation, we can find the specific model. And what we try to achieve is to propose a workflow to integrate it in the platform, testing it in specific situation, calibrating it, and all those pieces of work you've done is quite tremendous. Maybe I'm not going to say the best contribution of your work, but one of the most interesting is not even the more than 10 publications you've done, not the IPEXing framework on TTC and STM, but you've shown also that science is a worldwide contribution. You've come from Vietnam, working in Toulouse, work with people from Germany, from Lyon. Today we have people from Japan, so you've shown that science is a matter of collaboration, and I'm pretty surprised by the capacity to work with people who've been at the initiative of many of the work. So for all of that, I'm really happy to work with you. I'm pretty sure that you have a great career ahead of you. Thank you.
Thank you. Thank you.
Okay, so thank you very much. So Nicolas has put the context. So basically, I would say that, so first of all, thank you very much to all of you to coming, to accepting to be in the jury and to come here, being on site. So thank you too for this work. So, contrary to Nicolas, the start of the work is not starting with Madras project, but was before COVID, so 1 year before COVID. When we start to work on building some interactive table for irrigation simulation, so it was a long time ago, almost 5 to 6 years now. And yeah, when we have this project and when we have this PhD position, I was very happy to apply on it. So I was very confident that you can make a very good thesis and PhD work. What I was not expecting is what you will do. So as Nicolas said, you have a subject at some point at the beginning, and because thanks to the project, the subject you choose become larger than that one. So for all of the PhD students, so thank you also for PhD students to be here. We say them at the beginning that that's your work. You have a starting point, and you need to define your own subject and be master of your PhD, and that's exactly what you did. The deep learning approach was not planned at the beginning. The work, so much work on the dataset was not planned, so that's great that you can integrate the subject and sort of build your own subject with what you want. It was a pleasure to collaborate with you, and Madras project also very happy to collaborate, and we make a lot of connection with all the other PhD students. So that was great. The work was great. There were many publications. Perhaps sometimes not too much. In the current state is not perhaps good to say, but yeah, it was a great job. In your acknowledgement, you said that now my journey is about to end. So it was the journey of the PhD, but I think and I'm confident that it's not the end of the journey, but just one step, and you will come back to Vietnam as you want, and I'm pretty sure you'll find a good position, and I very hope to continue working with you on this topic or perhaps something
Why?
Thank you. Thank you.
Thank you. So, now the addition of the defense, the word is open to the public for questions, but the